Welcome back to NANDGAME. We are very near the end in floating point arithmetics. It's a long one. Let's get started. Unpack floating point value. This is considered an advanced subject. Floating point numbers can represent fractions and a large range of numbers compared to integers. This is achieved by including an exponent part which scale the base number up or down, corresponding to moving the bits left or right. We use a 16-bit floating point format, which uses 10 bits for the significand, 5 bits for the exponent, and 1 bit to the sign. The first mission is unpacking the 16-bit format into these 3 components so that we can perform further operations. Okay, so we have to unpack this 16-bit value here at the bottom. So if we need to unpack it, let's just start by grabbing a bit splitter here and hooking that up. And then we can look at the format here. Bit 15 is the sign, 0 is positive, 1 is negative. Looks like we can hook that just straight in. Bits 14 through 10 is the exponent. So I wonder if we can just take a bit bundler and then just hook up them directly like this, and then hook up that bundler to the exponent. We'll see if that works. Gonna move this one over a bit. And bit 0 through 9 is the normalized significand. Normalized significand means the 10-bit significand is assumed to be prefixed with a 1 unless the exponent is 0. In the unpacked format, this 1 should be inserted so we get an 11-digit significand. Let's start by grabbing another bundler, and we will hook that up just like we did with the exponent part. And then in bit number 10 here, we want it to be 1 unless this exponent section is 0. So I guess we can grab an is 0 flag and just hook that up to the exponent. And then I think we can just negate that, because if it is 0, this will flag 1. So if we negate it, if it is 0, it is 0. And if it isn't 0, then it's 1. So we can hook that straight in there. And then I think we can just hook this significand part up. Try to pin it to make it look slightly neater. And I believe this should work. Let's check solution. Oh, whoops, I used an is negative component here instead of a negate. That is my fault. I need an inverter here. Let's try that again. There we go. Yeah, you gotta grab the right component. That is important. Floating point multiplication. In floating point arithmetic, multiplication is simpler than addition or subtraction. So we start with multiplication. Floating point numbers are multiplied by multiplying the significands and adding the exponents. Multiplying two 11-bit significands as if they were integers will result in a 21-bit or 22-bit significand, but we need to compensate for the implicit point. So discard the 10 rightmost digits. This is one example where floating point operations may result in loss of precision while still giving a result of the correct magnitude. Yeah, you see that a lot in languages like Python, for example. When you do math with fractions, you'll often see this floating point in precision. Something to be aware of if you're doing any programming. Okay, so multiply two unpacked floating point numbers. So we kind of saw this last time. SG is the sign, EXP is the biased exponent, and SF is the significand. Okay, sign of the result should follow standard rules of multiplication. So real quickly, we'll jump into the whiteboard and design a sign multiplication truth table. Remember that 0 is positive and 1 is negative. So 0 and 0 multiplying two positive values gives you another positive value. 1 and 0 multiplying a negative value by a positive value gives you a negative value. Same thing the other way around. Multiplying a positive value by a negative value gives you a negative value. And then multiplying two negative values gives you a positive value. Okay, so what component does this truth table remind you of? Well, if you're thinking XOR, you are correct. So let's go back here and see if we have an XOR. We do. We'll hook up A to the first sign and B to the second sign, and then just output that result. So 0 and 0 output 0, and the other ones seem to follow the same logic that we showed off in our whiteboard. 1 and 0 is 1, and 1 and 1 is 0. So that should suffice for the sign. On to the exponent, which should be the sum of the exponents minus the bias, and the bias is 15. So we should be able to just add these together. A goes into the first exponent, B goes into the second, and then we need to subtract that sum minus 15, and I believe, yeah, we have a constant here. So we have to enter it in hexadecimal, and in hexadecimal, 15 is F. All right, and let's hook up that to the subtract. And it looks like the significand should be a product of the two significands. And if we read down here, it looks like we have a special component just for this level to deal with that. That's mul here. So we'll hook up A into the first significand and B into the second one. Now we can't just hook it straight up to the output here because we have to discard the low 10 bits of the product. So we have to run it through a bit splitter. And again, there's a little note here that we have a special 22-bit bit splitter. Hook that in. We'll take a bit bundler here. And again, 0 through 9 can be discarded. So starting with 10, we'll hook these up. Move this over to make it look a little prettier. And we have our 12-bit number here. Hook that up. And I believe this should work. Let's try it. There we go. Not too bad. Moving on. Normalize Overflow. The result of multiplying two significands may result in 11 or 12 binary digits. In the case of 12 digits, we normalize this to 11 digits by discarding the lowest bit and increasing the exponent by 1. So in the case of 12 digits, it should be shifted to 11 digits and the least significant bit discarded and the exponent increase with 1. So we need a bit splitter right off the bat because we need to see if this 11th bit, which is the 12th digit, is a 1 or a 0. That's going to be our flag to see if we have to shift everything and increase the exponent by 1. So we'll hook that up, and then we're going to grab a select 16. We'll hook the switch up from the select to the 11th bit there. And if this 11th bit is 0, we just want to pass the significand directly to the output. So we'll hook up D0 to the significand, and then hook that up to the output. If this 11th bit is 1, then we're going to have to shift everything over. So let's grab a bit bundler, and we'll hook up 10 to 11, 9 to 10, 8 to 9, and then so on down the rest of the line. And then this least significant bit, the 0th bit, just gets discarded, so we don't have to hook it up to anything. And then we'll hook this bit bundler up to D1. So that should deal with the significand. Now we need to deal with the exponent part. We'll take another select and again hook it up to the 11th bit here to see if it's 1 or 0. If it's 0, we can just directly funnel the exponent to the output. So we'll hook up D0 to the exponent and then hook up that selector to the output. But if it's 1, we want the exponent plus 1 to be funneled to the output. So let's grab our add here and we'll add our exponent, and then let's just grab a NAND since that outputs 1 if it's not hooked up to anything, and hook up our B value to that. So that should be our exponent plus 1, and then we can hook that up to the D1 of our selector here, and this should work. There we go, level successfully completed. Possibly this looks a little messy with all the crisscrossing wires, but I don't think it's too bad. Let's move on. Verify exponent. If the exponent is outside of the range 0 to 30, it should be set to 31. All right, so it looks like we don't have to do anything with our significand here, so I think we can just hook that up directly. And let's sort of just pin it over to the side just to get it out of the way. So let me reword this a little bit differently. If the exponent is 0 to 31, it should just go directly to the exponent output. If it's 32 or higher, then we just set it to 31 and send it to the output. So I think this would be really easy to do if we had a subtract component, but it looks like we don't have one here. So instead, we're going to grab a bit splitter and hook that up. So 31 in hexadecimal is 1F. And you can see in binary, our bits 0 through 4 are all 1 here. And anything above that, say 20, and that's hexadecimal 20, which equals 32 in decimal, we'll have the 5th bit or some other bit above 5 on. To put another way, if any of the bits 5 through 15 here are a 1, then we want to reset our exponent to 31. Now, I don't think our exponent will ever be big enough to flip one of these higher bits here past 5. So I think we can just use this 5th bit as a flag. So let's grab a select 16 and hook up our selector to this 5th bit. Now, if this 5th bit is off, meaning if it's 0, we just want to funnel the exponent directly to the output. So D0 should go to the exponent input, and then we can hook up the selector to the output. If it is on, then we want to funnel the number 31 to the output. We have a constant here. 31 is 1F in hexadecimal, so we'll hook that up to D1. And that should pretty much do it. Let's try it. Oh, and of course, we weren't really taking into consideration negative values. So instead of hooking the switch directly up to this 5, we'll grab an OR, and we'll say, if the 5th bit is on, or the 15th bit is on, which would denote a negative value, then we want it to output this constant of 31. Let's try that again. There we go. All right, and here it is rearranged to be slightly neater, but a pretty straightforward solution here. Moving on to align significands. Adjust the exponent and significand for two numbers so they share the same exponent. The common exponent should be the highest of the input exponents. The number with the lower exponent should be adjusted to the same exponent, which may require discarding digits of the significand. So let's start with our exponent. And previously we had built this max component, so that should make finding the highest exponent very easy. We'll input both exponents, and that will just output whichever one's bigger. So we can just hook that directly up to the exponent. Now then for the more complicated part, which is aligning the significands, it looks like we have a shift right here. We're gonna need that. What we want to do is shift the significand with a smaller exponent over to the right, and I believe we want to shift it by whatever the difference is between the exponents. So we have our max value here, and let's subtract the first exponent here. And then we're going to hook that up to a shift, and likewise hook up our x to the first significand. Now if this first exponent is the bigger one, then this subtraction should result in 0. We funnel it through our shift right here, and that's fine, we're just not shifting it over. If it's the smaller one, well, then we get the difference between the max and this exponent, and then it'll shift it over the appropriate amount of values. So we should just be able to hook that directly in, and then repeat the process for this b significand. Take a subtraction, and the a value will be the max, and the b value will be our b exponent. We will grab a shift right. The result of this subtraction should be the amount we have to shift it over. Hook that up to our significand, because that's what we want to shift, and then hook that up to the output. I think this should do the trick. Let's try it. Okay, add signed magnitude. Add or subtract two signed integers. SG is the sign, 0 for positive and 1 for negative, and M is the number without the sign. So -2 would have a sign flag on, and then M would be 2. And then we have an opcode that determines whether we're going to add or subtract. Okay, so this shouldn't be too tough. First, let's deal with getting these M values, A, M, and BM, to be positive and negative, depending on whether this sign flag is flipped. So let's grab a couple selectors, one for A, one for B, and we'll hook up the select to the sign bit here. Now if the sign is 0, it's positive, so we can hook our D0 directly up to M. If it's 1, it's negative. So how about we just use a subtract? We won't hook up A, but we'll hook up B to M. So it'll be 0 minus M, and that should give us the negative value of M, and we'll hook that up to D1. And we'll do the same thing on this side. Take a subtract and hook it up to the n value, and then hook D1 up to that subtract. So now if we have 1 here, we can just turn it positive and negative, and that'll reflect on the output of our selector. And then we just need to add or subtract based on this opcode flag. So how about we grab an add component and a subtract component. We'll add these two together through the add, and we'll subtract A minus B with the subtract. And then we're just going to need another selector to choose whether we add or subtract. So if this opcode is 0, we want to add, so we'll run D0 through our adder here. And if it's 1, we want to subtract, so we'll run D1 through this subtract. And we're just going to pin this around, kind of keep it out of the way. Now this select will output the value of whatever operation we're doing, but we're not just putting that directly to the output. We need to split it off again into the sign and the M, the magnitude. So to get the sign should be pretty easy. We can just get this is negative component here, hook it up to our selector, and if it's negative, it'll turn to 1. So we can just hook that up directly, and that'll give us our sign output. And then to get the M, the magnitude, that would be the value without the sign, we can use this flag again. We'll grab another selector. Let's put it over here. Actually, we're gonna kind of condense these a little bit to give us more space to work with. So we'll hook up our selector to this is a negative component. Now if the value for operation is positive, this is negative flag will be 0. And we can just funnel that directly to the M output. So we hook our D0 directly up to the selector, and M can just go right from the selector. Now if the value of our operation is negative, we actually have to turn that positive. Now there might be multiple ways of turning a negative value into a positive in binary. I think the easiest is we are just going to invert all the bits and then add 1 to it. We could use this add component, but we do just have an increment component, which should just add 1. And this inversion and increment should turn our negative value into a positive. Hook that up to D1. And this should be all that we have to do. Let's check it out. All right, another one that's a little more complicated, but not too bad. Let's continue on. Normalize Underflow. If the input significand has less than 11 digits, it should be changed to 11 digits, and the exponent adjusted correspondingly. And assume the input is non-zero and at most 11 digits. So what we're being asked to do here isn't too complicated. We're looking at the significand here. So if the significant value is 53, that's hex value 53, it only has 7 digits, and we need to left shift it over so that this 10th bit is a 1. And I believe for our exponent, where it says we have to adjust the exponent, all we have to do is subtract 1 every time we shift it over. The problem here is I don't see a lot of components that make this task easy. We only have single shift left, we don't have our barrel shift available, and like I said, we're gonna have to subtract from our exponent, and I only see an add here. I don't even see our subtract component available. All right, let's start simple and let's just add a left shift to our significand here. In fact, let's add 10 of them because we might need to left shift it over 10 times. Let's just get that part built. All right, we've got that set up. All right, and let's grab this bit component. And I think what this will do will tell us if a certain bit is 1 or 0. So let's try just adding 10 here because that's the bit we care about, the 10th bit, and hook it up here. And just kind of pin this along the side for simplicity. And I think we're going to need 10 more of these as well. All right, on second thought, I think I am actually going to use the bit splitter here because it's actually a little bit easier to use. And maybe, I mean, lengthwise it's bigger, but I think overall it's more compact than the bit splitter component that's built in here. So we're going to get rid of these. All right, so I've got this all set up, and actually I do like this bit splitter a little bit better because all we care about is this 10th bit, and I can stick most of this component off the screen because all we're looking at is this 10th bit over here. It is kind of messy looking. I think that's unavoidable here. Hopefully I've set this up properly so that I don't have to come back and try to fix anything. But what we're actually looking for here is the first instance where bit number 10 is a 1. So if the 10th bit from this first bit splitter, the one that's coming directly from the significant input, if that's a 1, then that's the one that we're going to want to funnel to the output. So we grab our selector, hook it up to the 10th bit in our first bit splitter, and if that 10th bit is a 1, then we want to funnel our significand right to the output. If it's not, then we're going to want to funnel the next value. So let's grab another select 16 and hook it up to the 10th bit of our second bit splitter here. And if that 10th bit is a 1, then we want to funnel the result of our first shift left to the output. And we're going to hook that up to D0. Grab another selector, hook it up to bit number 10 of our third bit splitter here. If it's 1, then we want to funnel the result of our second shift left. And then we're going to hook the output up to the D0 of the previous selector. And then we're going to repeat this process for all of them. And that's how we're going to funnel the correct number of shifts to our output. It's all hooked up. I believe it's working. You can see our last select 16 here. The D0 isn't hooked up to anything. That just means we've shifted it left 10 times and we still don't have bit number 10 as a 1, which would essentially mean our value is 0. And since we're assuming we're not going to get 0 based on our instructions here, we're just not going to hook it up to anything. And that should be fine. But you can see here, it does actually work. We have our value 1, 0, 1, 0, 0, 1, 1. And if you look up at our output, we've shifted it over and the 10th bit is a 1, and that should work exactly how we want it to. We can try just putting a 1 in here, and you can see it shifts that 1 all the way to the 10th bit. We can try a value like 1, 0, 0, 0, 0, and you can see we still get it shift to the 10th bit. So that's the significant part all worked out. It looks super messy the way these things are all connected, but just based on our bit splitter component that's kind of messy, I don't think there's a neater way to do it, so we're just going to go with it. Now we got to deal with the exponent part, and luckily we should be able to piggyback off what we've already built to some degree. Like I said, we're just going to have to subtract 1 every time we left shift. Now, if we had a decrement component, that would make it a lot easier. Unfortunately, we only have an increment 16, but I think that will work. And we're actually going to grab 10 of these because we have to decrement every time there's a left shift, and we only are shifting left potentially 10 times. So we should only need 10 increments. Okay, and we're actually just going to hook them up to each other. And then we're going to use another set of selectors just like this to cascade the proper result, the proper amount that we're shifting. We're going to then take that value and subtract it from our exponent before we output it. So let's go ahead and grab 11 selectors. This is going to get crowded. And we're getting to the part where this is very hard to understand what's going on. I am trying, I promise, but it is just hard to organize this in a way that makes sense. Maybe if I move some of these around, maybe that'll help it make it a little bit cleaner. All right, so we're doing the same thing on this first selector here. We're gonna check the value of the 10th bit of this bit splitter, the one that's not being shifted at all. If it's 1, actually, we don't need to hook that up to anything because we want to output 0. It means we haven't shifted at all. Then we'll take this second one, we'll call this the second one, hook that up to the bit splitter for our 1 shift left here. And if that is a 1, that means we want to shift left once. So we'll hook it up to this first increment that is a 1. Hook up D1 there. And then on the previous one, we have to hook up D0 to that second selector. Again, we're cascading just like we did before. We'll continue on. We'll hook up this D0 right to this. We'll call this our third selector here. Hook it up to our third bit splitter, the 10th bit there. If it's 1, we want to shift it over twice. We'll hook it up to the 2 increment. And if it's not, then we want to go to the next one here. All right, I'm going to keep cascading and hook them all up. Okay, so they're all hooked up, and you can see this first selector here, the output is 6. That's exactly what we want, because you can see here our hex value, we're shifting it over 6 times to get from this significand to this significand. So now we're just going to need to subtract 6 from our exponent here. Now the only problem is, again, we are not supplied with a subtract. Quite annoying, but we can turn this 6 negative by inverting it and then adding 1. So we do have an invert 16 here. And we only need to squeeze in 2 more components. We need another incrementer here. And then finally, we need an add. And the B value can come from this incrementer here. Again, that is the cascaded value. We're inverting an increment in order to turn it negative. And then the A value will be our exponent all the way down here. And the sum should just be able to hook up to the exponent output. Whew, that is a lot. It is kind of crazy. Hopefully my explanation made sense, because I don't think that you can kind of decipher what's going on here based on all this wiring. I really hope it works. Let's try it. Yes. All right, level successfully completed. Probably the better thing to do here would just be to create custom components. I am trying to solve these levels without custom components, which is why I have this mess. But it works. This is one of the tougher ones to deal with just because of all the things we needed to do. Even though at the end, what we're asked to do is simple. We're just shifting the significand over, so it's 11 digits, and then subtracting however many times we shifted from our exponent. Let's move on. Pack floating point value. Normalize and pack sign, exponent, and significand into a 16-bit floating point format. So we did the opposite thing at the very beginning, where we unpacked a floating point value. Now we have to repack it. We have our input sign, exponent, and significand, and we're going to have to pack it together in a 16-bit output. So we're going to need a bit bundler. We'll hook that up to our output, and then the sign should be the very easiest part. It just hooks directly in. We'll pin it over here just to get it out of the way, but very simple. Bit 15 is the sign. And then we have some other conditions about what to do if it's 0 and dealing with overflow and underflow. But let's not get lost in the weeds here, because we already did this. If you look in our components, we have this Normalize Underflow and Normalize Overflow. We built these. Let's just hook them in. Exponent goes to exponent, significand goes to significand, and now our underflows and overflows are normalized. Simple as that. We also have to normalize the exponent. Again, we already did that with this verify exponent, and we'll just hook that in. Exponent to exponent, significand to significand. And let's bring it down here just to give ourselves a little more space. And that's the hard part, really. The rest of this is just getting the exponent into bits 14 through 10 and the significand into bits 9 through 0. So we'll grab a couple more bit splitters, one for the exponent and one for the significand. Let's start with the exponent. We want this exponent to go from bit 10 to 14. So we're just going to hook these up in a row just like this. And that should take care of the exponent. In the significand, we want to hook up to bits 0 through 9. So we'll just hook up just like this. Bit 3 to 3, bit 4 to 4, all the way up to bit 9. And that should be it. Our unpacked floating point at the bottom has been packed up to the output. Let's try it. There we go. Level successfully completed. Moving on. Multiply 2 floating point numbers in the 16-bit packed representation. Okay, this should be easy because we built our multiplication already. The only issue is that our input has packed floating points and our output has a packed floating point. We're going to have to unpack each one. Not a big deal because we have the components to do that already. We'll unpack A, unpack B, and then just hook these straight in to our multiply component, just like so, making sure the sign, exponent, and significand are hooked in properly. And then we have our pack component, just hook those up straight in again, and then we can hook that up to the output. Very straightforward. Let's check solution, and there we go. On to the final level of floating point arithmetics, floating point addition. Add or subtract two floating point numbers. The op flag determines the operation. Once again, our input, we have two packed floating points, this time with an opcode, and then our output is, again, a packed floating point. So we know we're going to have to unpack each of these, so let's just do that straight away. And then we have our add signed magnitude component that we built earlier. But before we can add these two together, we have to make sure that their exponents are aligned. If their exponents are different, then we're basically trying to add things that have different orders of magnitude, and that doesn't work. So I'll input our exponents from each one, input the significand, and then I'll output essentially two new floating point numbers, but the exponent is the same for both of them, which is why we only have one exponent here. So we really just have to add the significands. So we'll hook those up into magnitude. And then we have to hook up the sign down here from the unpacked value, and we will do the same thing over here for our B value, and then hook up the opcode to this component as well. And now we've added our significands. So what do we do with this exponent? Well, we'll deal with that when we repack. Grab our pack component here. We'll hook up the significand to the magnitude and sign to sign, and then the exponent will come out of our align component. And we'll try to pin this over so we can see it a little bit better. All right, and then that should just go to the output. And this should be everything we need. Just funneling things through the proper components. Not too bad. Let's try it. There we go. All levels in floating point arithmetics completed. That wasn't too bad aside from our Normalize Underflow component, which was a bit crazy. Even though dealing with floating points is a pain, breaking up into these pieces makes it a lot easier. And next time we'll do multitasking CPU. I'm really not sure what all this is. They're all labeled as previews, so hopefully everything's working. Hopefully everything is straightforward. We'll find out next time. See you then.